I'm Anil Kumar. Welcome to my series on functions. This is prerequisite for calculus, and I hope these concepts will help you sketch functions in a better way, especially rational functions. We'll take up many examples related to vertical, horizontal, and oblique asymptotes. Let us first understand what are these asymptotes. Vertical asymptote may exist at the value of x that makes the function undefined. Now the key word here is that may exist, right? The second one here is whole may exist at the value of x that makes the function undefined. So these two things one need to understand fairly well. Let me take an example to illustrate. So if I have a function, let us say the function is, let's take very simple example. Let's say y equals to 1 over x minus 1. In this case, this function will be undefined at x equals to 1, right? So at x equals to 1, we are going to have a vertical asymptote. Vertical asymptote really means that when the x value is approaching this value, then the value of the function will be either positive infinity, approaching positive, or negative infinity, right? So if I am approaching, then from the right side it will approach positive infinity, and from the left side it is going to approach negative infinity, right? So at this place we do have a vertical asymptote. We'll write this as vertical asymptote VA, we'll write, and the equation of this vertical line is x equals to 1. So that becomes the equation of vertical asymptote. Clear? So now let's get back to our definition, which says vertical asymptote may exist at the value of x that makes the function undefined. So x equals to 1 makes this function undefined, and the vertical asymptote does exist, whose equation is x equals to 1. Clear? Now let's take another example. So I'll just place it very close by, and this time we will have a variation to this. We say y equals to, we'll say x square minus 1 over x minus 1. Now x square minus 1 can be factored, and you can write this as x plus 1 times x minus 1, and in the denominator we'll have x minus 1. As you can see, x minus 1 cancel. So we get just x plus 1. Do you see that? So what we get here is just this is equal to x plus 1 with condition that x is not equal to 1, right? Since x equals to 1 makes it undefined. So again, the function is undefined. Do you see this? In this case also, function is undefined at x equals to 1. However, we do not have a vertical asymptote here. What we have is a hole, right? So in this particular case, we'll have a line x plus 1 with a hole at x equals to 1, right? So we'll have a line which is kind of like this with a hole here. Do you see my point, right? So that is a hole, not a vertical asymptote. So we have a hole, and this hole is at x equals to 1, the y value being 2, correct? So sometimes you have a hole, sometimes you have a vertical asymptote when the function is undefined. That is important to understand. And when do you have a hole? You have a hole when you have a common factor. So that is which cancels out. So that's key to understand. Is that clear? Okay. Now let's get to the horizontal asymptotes. Horizontal asymptote may exist in rational function if degree of numerator is less than or equal to that of degree of denominator. So we have set two conditions here, right? So what we're trying to say here is that if I have y equals to, let us say x plus 1 over 2x minus 1. Their degrees are same, right? So we'll have a horizontal asymptote, and in this case we have a horizontal asymptote whose equation will be, horizontal asymptote is what a function is approaching when x is very large, right? So the horizontal asymptote in this case will be ratio of the leading coefficients 1 over 2, right? So we say horizontal asymptote is at y equals to 1 over 2, right? So this is when the degrees are same. If we have the condition that y equals to, let us say we have x over x square here, right? So x square, let's say plus 1. Now in this particular case, degree of denominator is higher than that of numerator, and so we have a horizontal asymptote which will be y equals to 0, right? That is kind of important to understand. Now when we say horizontal asymptote, what are we trying to figure out? We're trying to see what happens when x approaches positive infinity. If y approaches a value L, then y equals to L is a horizontal asymptote. That is what we're trying to say. Is that clear to you, right? Now, this could be for x approaches minus infinity also, right? In that case also, y equals to L will be a horizontal asymptote. Now, it's very important to note here that since we have x approaches large positive or large negative value, we could have two horizontal asymptotes also, right? So that is also possible. Perfect. Okay. Now let's get to the slant and oblique asymptote. We'll specifically say linear asymptote. So the definition is a slant or an oblique asymptote, oblique linear asymptote, will exist in a rational function if the degree of the numerator is one more than that of the denominator, right? So one more than that of the denominator. So that is to say that for oblique asymptote, we are looking for a function like y equals to x squared plus 1 over, let us say we have x plus 3, something like this, right? So degree of numerator is 1 higher. So in this case, we'll get oblique asymptote. We'll soon understand how to figure this out. You have to perform long division. And the quotient is the equation, right? So quotient is oblique asymptote, right? Okay. Right. So that is how we'll get oblique asymptote in a rational function. Now it is important to note that all the exponential functions can have horizontal asymptotes, right? So that is important to understand. And logarithmic functions will have vertical asymptote. But generally, most of the time we're talking about rational functions when we discuss this topic on asymptotes, right? So it's important to understand that exponential functions will have horizontal asymptotes and logarithmic functions will have vertical asymptotes, okay? So with that note, let's take a few examples to practice and understand how to find these asymptotes. Very first example here is to determine vertical asymptotes for each of the following. So there are 6 functions given to you. You need to check 2 things. First, do we have a common factor between numerator and denominator? And second, is a function undefined for any value of x? That is, can the denominator be 0, right? That is the main question. So if you have to find vertical asymptote, the question is, can the denominator be 0? So that is the question which you need to answer. So let's answer this question one by one. So for the very first function, x equals to minus 1 makes it 0, right? So we have x plus 1 equals to 0. That means x equals to minus 1, right? And that means we have a vertical asymptote. So we have a vertical asymptote and the equation is x equals to minus 1. Is that clear? Second, We'll just equate 2x minus 3 to 0, and then we say 2x is equals to 3, x is equals to 3 over 2. And so we can say that there is a vertical asymptote x equals to 3 over 2. Clear? Next equation. This is absolutely clear. X square, x is in the denominator. So we have a vertical asymptote which is x equals to 0. Now here we have x plus 2 whole square. So we have a vertical asymptote, and that is at x equals to minus 2. If I substitute minus 2 here, we get 0 in the denominator, right? Now in this equation, we could have two different values for which the denominator is undefined. So the vertical asymptotes, there are going to be two. One is at x equals to minus 1, and the other one will be at x equals to 2 over 3. How do we find these values? Equate denominator to 0. Perfect. Now in this example, 2x plus x squared can be equated to 0. So let's do it. So we have 2x plus x squared, equate that to 0. X is common, so we get 2 plus x equals to 0. And that gives us two vertical asymptotes. One is at x equals to 0, and the other one is at x equals to minus 2. So for both these values, we have vertical asymptotes, correct? So as you can see, in these 6 examples, all of them had vertical asymptote. It is important to note that there is no common factor between numerator and denominator, especially with the term where the denominator becomes 0. And therefore, in all these cases, we have only vertical asymptotes. I mean, we are only considering vertical asymptotes for the time being. There could be other asymptotes also, right? So we are specifically only checking vertical asymptotes at present. Perfect. Okay, now let's move on and see slightly more in details about the vertical asymptotes. Here is question 2 for you. Now this is kind of typical, since this is not that straightforward as we had in question number 1. I would like you to pause the video, answer this question, and then look into my suggestions. Number 2. Determine vertical asymptotes for each of the following, right? So let us now factor and then check. So we have this function f of x as equal to 5x, and the denominator can be factored. We could write this as x times 1 plus 2x, correct? Now as you can see, x and x cancel. So we have a vertical asymptote, and that is only because of the factor 1 plus 2x, not because of x. Remember, x can also make the function x equals to 0, make the function undefined. However, it doesn't contribute to vertical asymptote, right? So in this particular case, we have a vertical asymptote, and which is at x equals to minus half, right? Now the factor which actually cancelled, that results into a whole, right? So we do have a whole at x equals to 0. Now if I put x equals to 0, we get y also as 0, right? So anyway, whole is at x equals to 0. Normally for whole, we give a coordinate point. So let me write 0, 0. So at origin, we will have a whole. Perfect. So let me change this question a bit. Determine vertical asymptotes for each of the following, or we can also mention wholes, right? Wholes slash vertical asymptotes, correct? So if the factors cancel, we get a whole. Now, next example, let us factor this also. So we get f of x as equal to 2 is common. So we get 3x minus 1. Denominator is 1 minus 3x and x minus 3. As you can see, once again, we can actually cancel 1 minus 3x and this with a negative sign, correct? So we could write this as equal to minus 2 over x minus 3. There are two restrictions here. So one of the restriction is into a hole, the other one is because of vertical asymptote, correct? Results into vertical asymptote. So here we have a vertical asymptote which is at x equals to 3, right? However, at x equals to 1 over 3, we have a hole, right? So we have a hole at x equals to when this factor becomes 0, right? Which is at 1 over 3. Is that clear to you? So this is kind of important to understand when we are talking about vertical asymptotes. Many times that part is missed. Let's look into the next example. So we can again factor this. Numerator can be written as x plus 1 times x minus 1 denominator. Okay, so it is x squared. Let's first write this as minus of x squared plus x minus 2, right? Now we can factor this. Okay, so we get x plus 1 times x minus 1. So here we have product of 2, so 2 times 1 will work. So minus x minus 1 times x plus 2. Right? 2 times 1, positive number is higher. So one of the factors cancel, the other one results into vertical asymptote. So we have a vertical asymptote and that is only at x equals to minus 2. However, we have hole at x equals to 1. Does it make sense to you? So you can substitute the value of 1 here to get 2 over 3 minus, which is going to give you the position of the hole, right? Okay. Next example here is f of x equals 2. Let's factor this. 3 times 2 is 6 and x minus 3 times x plus 2, right? So denominator being x plus 2 whole square. Now here again x plus 2 is a common factor, it cancels. But now you will notice that x plus 2 also remains in the denominator. So therefore, in this particular case, we do not have any hole, right? One factor cancelled, we do not have hole. However, we only have a vertical asymptote and that is at x equals to minus 2, right? Remember, note, no hole. Do you understand? So I cannot say that when the numerator and denominator factors cancel, you will have a hole. Here is an example which shows that maybe, right? So it's not always true. Now, let us discuss behavior of the graph of the function near a vertical asymptote. This is kind of very important strategy to understand, especially when we are trying to sketch a graph, right? So let me rewrite the function. The function before us is f of x is x minus 1 over x squared plus 2x. So I could write this as x minus 1 over x is common, so we get x plus 2. So that means we have two vertical asymptotes. One is at x equals to 0, the other one is at x equals to minus 2, correct? Now we'll try to see the behavior of the graph near these asymptotes, right? So we are not sketching the whole function, remember that. We are only trying to understand behavior of the function near the vertical asymptote, right? So one of the vertical asymptotes is at 0. So that is your vertical asymptote. The other one is at minus 2. So let's say this is the other one, which is at minus 2. So we have these two vertical asymptotes. This is x equals to 0 and that is x equals to minus 2. When we say discuss behavior of the graph of the function near the asymptote, it means what? It means that we are approaching the vertical asymptote from left and right side, right? So we are approaching from this side as well as on this side. So we're trying to figure what is the value of the function as we approach. Is it positive infinity or negative infinity, correct? So when the value of x is approaching 0, let's consider minus 2 first. Minus 2 from the left side. So this means from the left side, what happens? So that is the function. So in this particular function, if I substitute a value, which is negative 2.1, for example, right? So basically think like this. We now have a function f of x. We substitute some value, which is, let us say, negative 2.1 minus 1 over negative 2.1 times negative 2.1 plus 2. So we have to only check the sign. So as you can see from here, the numerator is going to be negative for sure. As far as the denominator is concerned, negative 2.1, but this negative 2.1 plus 1 is also negative. So negative is positive. When you do negative and positive, then the function approaches negative infinity, right? So we know this value, when you're approaching from the left side, is approaching negative infinity. So that is the behavior, right? So we can say that the y value, or f of x, approaches negative infinity. Do you see that? Now let's analyze what happens when x approaches negative 2, but from the right side. So right side means we can take a value which is like 1.9 minus 1.9. So let's substitute that and check. So it's kind of a test point, right? So if I write minus 1.9 here, minus 1, we know for sure numerator is negative. Denominator minus 1.9, and here we have minus 1.9 plus 2. Now this part is positive. So what we get here is we get negative and negative, right? So that results into positive infinitely large value. So from this side, it approaches positive infinity. Is that point clear to you? Correct? So that is called behavior near the asymptote. Now, let us consider the behavior when x approaches 0 from the negative side, means from left, right? So think about a negative value. So if I write a negative value here, this will be negative, that will be negative, this will be positive, right? So in this case, we know that the y value will approach, if I write a negative, let's say small negative value, in that case numerator is negative for sure, and denominator, this is negative, that is positive. So when you multiply two negatives, you get positive value, so that approaches positive infinity. So from the negative side, it approaches positive infinity. So the graph will be kind of like this. Similarly, if I substitute x value, which is greater than 0, positive value, then in that case, now since this is minus 1, 1 is much bigger than this small value, numerator still is negative, denominator positive and positive. So we are left with a negative value. So y approaches negative infinity, and we'll get this graph approaching downwards on this side. Does make sense to you? Correct? So that is what we are saying, behavior near the vertical asymptote. Is that clear to you? Perfect. Let's move on and now consider the horizontal asymptotes. Perfect. So I hope the concept about vertical asymptote is absolutely clear. Right. Now let us consider when do we have horizontal asymptotes and what will be its value. So in horizontal asymptote, we are always checking what happens when x is approaching a large positive or negative value, correct? So basic definition is that if x is approaching positive infinity and y approaches a value L, in that case there is a horizontal asymptote y equals to L. Now this is also true when x is approaching a negative infinity and y is approaching some value L, then also horizontal asymptote is y equals to L, correct? That is the definition. So we'll use the concept of limit, that is approaching, right? In other words. So we have three different conditions on this. Now here, when we have this kind of a function, numerator and denominator degrees are same. If that is the case, we can say for such condition, there is a horizontal asymptote, and the value of this horizontal asymptote is y equals to 3 over 1 or 3, right? So straight away, looking at it, we can give you the answer. The next one here, if you compare, degree of denominator is higher. Since that is higher, we do have a horizontal asymptote, and the equation is y equals to 0. In the third case, degree of numerator denominator is same. So the coefficients of leading coefficients ratio will be our answer. So we have a horizontal asymptote, which is y equals to 2 over 3. Is that clear to you? Right? So that is straight way of finding the horizontal asymptote. However, here is a method to do it. Method is something like this. We have 3x minus 1 over x plus 1. We could take x common. So let's rewrite this as limit x approaches infinity. If I take x common, I get 3 minus 1 over x over. Here if I take x common, I get 1 plus 1 over x. Correct? Now, x and x will cancel away, so let's cancel them. We are left with 3 minus 1 over x and 1 plus 1 over x. When x is very, very large, 1 over x is 0, right? So this is as good as saying 3 over 1, right? Since 1 over x approaches 0 for x approaching infinitely large value. So both these values will be approaching 0. You are left with just the number 3. So as x approaches infinity, the value of this function approaches 3, which is a constant value. Therefore, there is a horizontal asymptote y equals to 3. Does make sense to you? Correct? Okay. Now let's follow the same process for the next example. We have limit x approaches infinite, and here we have x, here we have x squared. So now let's take x squared common. So we have minus 2x over x squared, 1 plus 1 over x squared. Now in this case, one of those x's gets cancelled, you get x in the denominator. So when x is very, very large, that makes it 0, right? So what really happens is, this could be written as limit x approaches infinity, and what we have is minus 2 over x, right? Since that becomes very small, but this x results it into 0. So this also approaches 0. You get the idea, right? So when x is very large, it will approach 0, and therefore y equals to 0 becomes horizontal asymptote. Clear? The last one. Try it yourself, right? So we'll apply the same strategy. We write this as limit x approaches infinitely large, 2x squared minus 3x. So we can take x squared common. We are left with 2 minus 3 over x, right? And denominator, we have 3 x squared plus x minus 5. We'll take x squared common. We are left with 3 plus 1 over x minus 5 over x squared. Now clearly, x squared and x squared will cancel. When x is very large, these values approach 0, right? These values approach 0. And therefore, what are you left with? You are left with 2 over 3. So this approaches 2 over 3. Does make sense. So y equals to 2 over 3 becomes the horizontal asymptote. So that is how you could algebraically find the answer, but by simple inspection also, we can write down the value of horizontal asymptote. Perfect. Now let's take more examples. Question number 2 here. So we have learned the concepts about vertical asymptotes and horizontal asymptotes. We are going to apply that to answer this question. The question here is, for the function f of x equals to x over x squared minus x minus 6, determine the equation of all the asymptotes and illustrate the behavior of the graph as it approaches the asymptotes, right? So first, let's try to figure out the asymptotes. We have the function f of x equals to x over x squared minus x minus 6. So you can factor this. We get x over 3 times 2, right? So we get x minus 3 times x plus 2. Now, as the denominator degree is higher, we have a horizontal asymptote, which is y equals to 0, and we have two vertical asymptotes. One is at x equals to 3, The other one is at x equals to minus 2, correct? So these are the asymptotes. So let us actually sketch these asymptotes first. Let us say this is our graph paper. So on this graph, we have a horizontal asymptote, which is y equals to 0, which is x-axis, right? So that is the horizontal asymptote. Now the vertical asymptotes are at 3 and minus 2. So let's say this is 3 for us. So this is x equals to 3, and then minus 2 is somewhere here. So this is at minus 2, correct? So these are the vertical asymptotes. So we have identified all the asymptotes. One is y equals to 0, right? So this is y equals to 0, the x-axis. And these two vertical asymptotes. Now let's see the behavior. So let's first consider behavior near the horizontal asymptote, okay? So for horizontal asymptote, if x approaches large negative value, if x is large negative value, in that case what happens, right? So we have a negative in the numerator, this becomes negative, and in the denominator, this is negative, this is also negative. We have negative times negative, correct? So what we get here is negative. So we are approaching from the negative side, so that is kind of like this. So that is how we get the behavior. Do you see that part? Second, if x is approaching positive infinity, in that case, all of them are positive, right? This is positive, this is positive, this is positive. All these positive, when multiplied, will give you positive. And so on this side, it approaches from above the axis. So that is how it approaches. Does it make sense to you? Correct? Now let's talk about the vertical asymptotes. So let's consider minus 2. So when x approaches minus 2 from the left side, so from this side, correct? So this is negative. So in that case, f of x, this is negative, right? So we'll write numerator. This is negative. We have a value which is, let's say, think like this. We'll use minus 2.1 when approaching from this side. So if I write minus 2.1, this is going to be negative, and that is also going to be negative, right? So we have negative, negative, and 3 negatives will result in negative. So that is so simple. So we get this graph approaching this side here. Is that clear to you? Similarly, when I do x approaching minus 2, but from the positive side, think about minus 1.9. So in that case, numerator is definitely negative, since that is a negative value, minus 1.9, and this will be negative. However, that value is going to be positive. 2 negatives will give us positive, and therefore we are going to approach, when we are approaching from this side, positive infinity. Is that clear? So that is the technique of finding behavior near the vertical and horizontal asymptotes. So now I'd like you to try what happens when x approaches 0, but from the left side, right? So that means we are placing a value like minus 0.1. Now if that is negative, numerator is going to be negative. There's one x here, right? This negative, negative will be negative, and this is going to be positive. So we are left with 2 negatives, which will result into a positive, correct? So when you're approaching from the negative side, you are approaching positive infinity. So this will be the behavior. Do you see that? Last, if x is approaching 0, but from the right side, we write 0 plus. In that case, we have a positive number in the numerator, right? So we have a positive number here, but in the denominator, that minus 3 is bigger negative, and that is going to be positive. So we have one negative which results into negative, and therefore this vertical asymptote will be pointing downwards when you're approaching from the right side. Does it make sense to you? Correct? Likewise, we will now consider what happens to the value of y when x approaches 3 from left side. So when we are approaching from the left side, think like this: 2.9 is your value. Is that okay? So if I write a positive 2.9, then this value is positive in the top. Here it is negative, right? And this is positive, correct? So there are one negative, so that will give you negative value, and therefore the function is going to go downwards. Is that clear? On the other hand, if I have x value approaching 3 from the right side, all will be positive, correct? Which will result into positive, and therefore the function will go upwards in this fashion. So that becomes the behavior of the function near the asymptotes. Is that clear? Extremely important, right? Okay, now let's move on and talk about oblique asymptote. We also call them slant, right? They are at an angle like a straight line. So when do we have oblique or slant asymptotes? Whenever the degree of numerator is 1 higher. So in this case, key is numerator degree is 1 more than denominator degree. Clear? So that is the case. So in both these cases, we have an oblique asymptote, correct? There are other asymptotes, but we'll only focus on oblique asymptote. How do we figure them out, right? So the best way to find oblique asymptote is to do long division, right? So we'll perform long division to find oblique asymptote. So it is 2x squared plus 6x plus 5. We should divide this by x plus 2. So you get 2x times multiplies, we get 2x squared plus 4x, and when you take away, you get 2x plus 5. So you can multiply this by 2. So you get 2x plus 4, and the remainder is positive 1. So that clearly means that the line, now your function f of x, can be written as this quotient, which is 2x plus 2, plus this remainder 1 over x plus 2. So that is how you could actually write your function. So clearly we have a factor 2x plus 2, which is an oblique asymptote. It does make sense. So we have oblique asymptote, we'll write OS here, which is y equals to 2x plus 2. This particular quotient, that is the oblique asymptote, correct? So basically the graph is going to approach the line 2x plus 2. Is that clear to you, right? That is the whole concept. Now, let us do the next function also. Let's find out the oblique asymptote. Process is same. So we'll again divide the numerator, which is x squared plus x minus 7 by x minus 2. So it goes x times, you get x squared minus 2x, and when you take away, you get 3x minus 7. You will multiply this with 3, so you get 3x minus 3 times 2 is 6, and when you take away, you are left with minus 1. So in this case, it is minus 1 here. You could write this function f of x as equal to the quotient, which is x plus 3 minus 1 over x minus 2, correct? So we see that again we have an oblique asymptote, right? So in this case, the oblique asymptote is y equals to the quotient x plus 3. So that is how you can find equation of the oblique asymptote. Now we'll take up another video in which we'll discuss in more details of behavior near the oblique asymptote and then we'll take up how to sketch a rational function. Correct? Rational functions could have oblique asymptotes or vertical asymptotes, holes, and sometimes horizontal asymptotes. Perfect. So, knowing all this helps us to really sketch them fairly accurately. So, we'll take that part in the next video. However, I hope you got good concept about all these asymptotes, how we could find them, when will vertical asymptote exist, when will horizontal will exist, when will a slant and also we looked into holes, right? So these are the four things which are very important to understand, especially when you're sketching or talking about rational functions. I hope that makes sense. Feel free to write your comment, share your views. If you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.